Hello everyone. Today we're going to learn about hybridization of atomic orbitals. A quick review of electron geometry. The electron geometry for a molecule is the shape that depends only on how many domains surround the central atom. The electron geometry does not depend upon what kind of domains are present, just how many there are. As such, there are only 5 electron geometries that we have discussed previously. They are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, corresponding to 2, 3, 4, 5, and 6 domains respectively. Each of these also has common bond angles associated with them. For more information on that, please see a previous video. The thing we need to consider, though, is that generally speaking, bond lengths are equal, unless of course there is a double or triple bond involved. But if we consider a central atom with a certain number of bonds around it, those bonds are all of equal length experimentally. So for example, carbon usually makes 4 bonds, and those 4 bonds are usually equal in length, again, barring any double or triple bonds. Let's consider the electron configuration of carbon and locate where its valence electrons are. The electron configuration for carbon is 1s2, 2s2, 2p2. The 4 valence electrons of carbon come from the s orbital and the p orbitals. However, in the molecule, it appears they all come from 4 different orbitals, which is not the case for these atomic ones, and that those orbitals appear to be equal. But the s and p do not look or act like each other at all. So, something must be different between the atomic orbitals and the molecular ones used for bonding. The thing that turns the atomic orbitals into new molecular orbitals is called hybridization. Basically, what happens is the atomic orbitals are put together and combined into a new form, or hybridize, to create the molecular orbitals used for bonding. You should always consider how many molecular orbitals you're going to need when you're discussing how something is hybridized. The number of hybrid orbitals required will be equal to the number of domains, including any that might contain lone pairs. For example, a tetrahedral molecule, such as methane or nitrogen trihydride, would require 4 hybrid orbitals, despite the fact that methane has 4 bonding orbitals, and nitrogen trihydride, or ammonia, would only need 3 and then 1 for a lone pair. That lone pair is still going to go into a hybrid orbital. So, where do these atomic orbitals that we make the hybrids with come from? They come from the valence orbitals of the atoms involved. Usually we consider only the hybridization on a central atom, although hybridization is still occurring on the outer atoms as well. Hybrid orbitals have very strange names that are based upon what atomic orbitals were put together to create them. So for example, if we consider our tetrahedral molecules once more, in order to create the 4 that we need for the tetrahedral molecule, we're going to take 1 valence s orbital and all 3 of the valence p orbitals to make 4 sp3 hybrids, named for the 4 things that make it up, an s and 3 p. A quick reminder that when you deal with a set of orbitals, they have different numbers. A set of s, there is only 1. In a set of p, there are actually 3 orbitals that can each house 2 electrons, hence why the maximum for a p is 6. D, there are 5 orbitals, and F, there are 7. If you went out to a theoretical G orbital, the answer would probably be 9. So let us consider an example and determine the hybridization on the central carbon for formaldehyde, CH2O. The Lewis structure for this molecule is shown below. In order to determine the hybridization, we first must count the number of domains, and in the back of our mind, think what the electron geometry of this is. There are 3 domains here. There are 2 single bonds to the hydrogens and 1 additional domain that houses a double bond to the oxygen. So this is a trigonal planar molecule. We need to know what we need in order to hybridize it. So let's start at the beginning of the valence set. We can pull one of the 1s orbital that is on the valence set, and we need 2 additional ones, so let's take 2 of the p. So therefore, for formaldehyde, the central carbon is sp2 hybridized. In order to make the 3, I took the s from its valence set and 2 of the p. That does leave one p orbital that is currently not hybridized. We'll worry about what happens with that in a moment. A quick note, obviously when you break the octet for those with 5 and 6 domains, we need to consider what is beyond p, because sp3 is the most we can do, and that only gets us to tetrahedral. Theory has suggested that it should be d orbitals that we pull from for this. However, experimentation has not supported this in recent years. Until we have a better answer, however, we are just going to pull these d orbitals because we just don't have another answer at this time. Hopefully in the future, there will be a better answer to this. So for now, if we were to consider an octahedral molecule like sulfur hexafluoride, we would say that it is sp3d2 hybridized. We take the s orbital that's in the valence set, all 3 of the p, and 2 of the 5 d orbitals. Because of the electron geometries we are working with, this is the highest hybridization that you will find. You can also talk about hybridization on centrally located atoms in larger molecules by just looking at that individual atom. So for example, if we look here at one of the simple amino acids, let's determine the hybridization on the carbon marked carbon 1, the one on the left, in the molecule below. How many domains surround carbon 1? There are 3 domains: a single bond to an oxygen for a hydroxyl group, a single bond to its neighbor carbon, and a double bond to the oxygen. So it requires 3 hybrid orbitals to be created. A quick thing to note is that there are a couple different kinds of bonds that occur. The hybrid orbitals that we have been discussing are where sigma bonding occurs. These are our primary bonds that are the ones that are stereotypically thought of. How these function is that the orbitals on neighboring atoms physically overlap in their space and link together, kind of like the train cars linking together with their linkers. In these, the electrons are located in that shared space most of the time, and electrons are considered localized. They are trapped between their 2 atoms. They can only be found in that central space or possibly spending a little bit of time with one of their 2 atoms. Most bonds that we are going to deal with are sigma bonds. There are a couple of bonds, however, that are not sigma bonds. These occur with non-hybridized orbitals. I mentioned earlier, when you are sp2 hybridized, there is usually an open p orbital. This p orbital could participate in pi bonding. Non-hybrid orbitals participate in pi bonding when those orbitals are parallel to each other. So there is some weird spatial things and a lack of an ability to rotate that occurs when pi bonding takes place. In a pi bond, the electrons freely move or flow between the parallel orbitals. It is because they are acting over a relatively small distance for a bond, and because they are parallel, they are easily able to align and go back and forth between the 2, creating a bond that is weaker than a sigma bond would be, but is a bond nonetheless. The electrons here are considered delocalized because of the freedom of movement that they have been given, and thus there are some unique properties that come in with having delocalized electrons. Where these bonds occur are in the additional bonds for double and triple bonds. So that second bond that creates the double bond and the second and third bonds in a triple bond are considered pi bonds. Please note this means the first bond for each of these is a sigma bond. So if you consider a double bond, one of them is sigma and one of them is pi. It is important to be able to count how many sigma and pi bonds are present in a molecule. So let's look again at our simple amino acid here. We must determine the number of sigma and pi bonds. Pi bonds are probably the easiest to count. We have to look for anywhere where there are double or triple bonds. I see one location for a double bond. One of those bonds is sigma, so we'll ignore it, but one of them is a pi bond. So there is one pi bond in this structure. The sigma will take a little bit longer to count. There are a total of 9 sigma bonds in this molecule. Unfortunately, 3 of them are not really drawn. There is a sigma bond between the H and the O on the far left, and there are 2 others between the H's and the N on the far right. In addition, that makes 3. In addition, the O to the C from the OH group on the left is another. The first one of the double bond to the oxygen was a sigma bond. The one linking the carbons together is a sigma bond. The one that links carbon to nitrogen is another. And the ones that link the carbon 2 to each of its hydrogens are also sigma bonds, giving a total of 9. And as we previously mentioned, there is only one pi bond in this completed structure.